Welcome to our SC1015 mini project on breast cancer prediction. Our group consists of Wayne Tan and Changming Han. This is the presentation flow for today. Kicking things off with the problem formulation. Now, breast cancer is a very pertinent problem in the modern world, with many deaths worldwide, and furthermore, 1 in 8 people in the US develop breast cancer at some point in their lives. To make matters worse, it is the most prevalent cancer among women in Singapore. 1 in 13 women will get breast cancer at some point in their lives. As such, more needs to be done to tackle this problem with the resources and techniques we have. Identifying some of the gaps in the current diagnostic methods, we realize that breast cancer prediction is actually very taxing on doctors, generates millions of errors worldwide, and the current screening processes are far from perfect. This led us to arrive at the practical motivation. We realized that the diagnosis of breast cancer is actually a data-driven problem. Ultimately, a medical professional should still confirm the results, but machine learning techniques can still augment the process by improving the initial prediction phase. This is the final problem statement that we have. How can we use machine learning models and a patient dataset to classify and predict breast cancer to provide a reference for the early diagnosis of breast cancer? Exploring the dataset which was obtained from Kaggle, it consists of 30 predictor columns that were split into 3 categories: mean, standard, and worst. We chose the 10 columns under the mean for this project, and we had 569 rows to work with. Moving on to the data cleaning and preparation phase. Now, the goal of this phase is to remove the outliers and to select the top 5 features as the best 5 predictors for the response of the breast cancer prediction. To achieve this goal, we have finalized on 3 steps: data visualization, outlier removal, and feature selection. Allow me to walk you through the steps of this process. We first started off by dropping redundant columns. Next, we focus on outlier removal by looking at the box plots for each of the 10 features. Let's take a look at the box plots. We see that there is a significant number of outliers for each of the 10 features. We went ahead and removed them and confirmed that there are indeed very little outliers left. This brings me next to the skew analysis. Now, this could be quite important since skewness can lead to inaccuracies, particularly in the models that we are using for this project. Looking at the histograms, we realize that there are actually a few variables that exhibit some level of positive skewness, which might be concerning as it might indicate that these variables are not suitable for prediction. However, this is only an initial sensing, and in order to arrive at a more convincing answer, we have to dive deeper using further techniques. This brings me to the feature selection phase. It consists of 2 parts. The first part is by looking at the swarm plots. Now, we aim to identify the top 5 predictors by looking at those which has the least overlap between the benign and malignant box plots. We have identified 5 such features, and they are the radius mean, concavity mean, concave points mean, perimeter mean, and area mean. However, this is only the initial sensing. In order to confirm these results, we performed an ANOVA hypothesis test using the SciPy-Stats model. Now, the p-value is defined as the probability of obtaining a result equal to or more extreme than what was actually observed. And thus, by running this ANOVA hypothesis test, we chose to rank the top 5 features based on the smallest p-values obtained. These are the results we got, and the smallest 5 are indexed 0 to 4. Interestingly enough, these 5 results correspond with the top 5 selected earlier, and therefore, this will be our final 5 predictors for this project.
Next up, we will look into the various machine learning models that we chose for our project. In this project, we chose to go with the decision tree classifier, logistic regression, random forest, and support vector machine with grid search. These models were carefully selected from a wide variety of models based on several task-specific factors which we deemed as important. Our model selection was done based on 3 main factors: dataset types, interpretability, and performance. The dataset that we used was the breast cancer dataset, which contained mostly continuous variables. As stated in the problem statement, our goal was to predict whether a patient was breast cancer positive or negative, which is a categorical variable. Secondly, because the model is meant to be used in a medical context, it is important for the model to be interpretable, where the model can provide explicit rules or coefficients that can be easily understood and explained. This is compared to deep neural networks, which are less interpretable as they involve multiple layers of abstraction. Lastly, The model needed to perform well on metrics which were used for validation in the healthcare industry. These were metrics such as the receiver operator curve, as well as other coefficients such as the F1 score and recall. Overall, the models were also evaluated based on conventional metrics such as classification accuracy and precision. The first model that we chose was a decision tree, which is a graphical representation of the decision-making processes or decision rules that can be used to predict outcomes based on input features or variables. Decision trees are widely used models as they are easy to use since they do not require complex calculations or intensive computational resources. Furthermore, they also perform automatic feature selection, whereby the model automatically selects important variables from the input data. Lastly, and perhaps most importantly, decision trees are highly interpretable, which is a much valued metric in the healthcare industry. What follows from the decision tree is the random forest model, which is an ensemble learning technique which combines multiple decision trees to create a more accurate and robust model. Compared with a single decision tree, it is known to produce greater accuracy and be more resilient to overfitting due to bootstrapping and random feature selection. The next simplistic model that we chose was logistic regression, which is essentially another generalized linear model procedure using the same basic formula, but instead of the continuous y, it is regressing for the probability of a categorical outcome. In the simplest form, this means that we're considering just one outcome variable and two states of that variable, either 0 or 1, which ultimately results in a sigmoid curve. This model is also versatile and is able to be used for a wide range of binary classification tasks. The most complicated model we used was the support vector machine, which is essentially a model aimed at finding the hyperplane that best separates the features into different domains. SVM is used for smaller datasets as it takes too long to process, and this was applicable here as our dataset was relatively small. SVM is also excellent at dealing with nonlinear data as a result of their inbuilt polynomial, radial basis function, sigmoid, and other various kernels. Lastly, the greatest advantage SVM had over the other models were the few hyperparameters that it had. This allowed us to do a simple grid search across all the hyperparameters to determine the best settings for the model. Finally, after implementing all the models on our breast cancer dataset, let's take a look at some findings and insights that were derived from the different models. Over here, the receiver operator curve is a graph showing the performance of a classification model at all classification thresholds. The area under the curve ranges in value from 0 to 1, and a model whose predictions are 100% wrong has an AUC of 0, one whose predictions were 100% correct has an AUC of 1. In this graph, the red line shows the performance of a random classifier, where the classifier has a 50% chance of making the right guess and a 50% chance of a wrong prediction. The perfect classifier is the case whereby there are 0 false positive cases and all positive cases are correctly predicted. The colored lines in this graph show how the models perform on the breast cancer dataset, with the most important metric being the area under curve, which will be compared along with other metrics in a later slide. Over here, this table shows a comparison of all the models we used in our prediction of breast cancer. Classification accuracy is defined as the total number of true positives plus the total number of true negatives over the entire dataset size. Next, the F1 score is defined as the harmonic mean of precision and recall. It has some advantages over classification accuracy metric as it is designed to work well on imbalanced data, which is characteristic of our chosen dataset. Now, let us visualize this data by viewing a bar plot of the various models. From the bar chart above, we see that the random forest classifier has a higher classification accuracy, a higher area under the curve of the ROC, and a larger F1 score than all the other models. This makes the random forest classifier the best model in predicting breast cancer. Our key recommendation lies on the fact that the breast cancer dataset is rather small. As such, this may not be indicative of a highly successful model. Though we achieved 95% accuracy with a random forest classifier, we believe that the models can be made more robust with training on larger and more extensive datasets. Next, automatic tuning of the hyperparameters using informed search strategies can also be implemented over grid search or random search to reduce training time. This will enable greater data processing throughput, which could help improve the models in the long run. With that, we thank you for your time and present to you our references for this project.